Okay, I'm giving you 10 seconds here. Just observe and tell me what you understand.
Can I tell?
Okay.
Electronic polarization,
Mm,
ionic, and
mm,
the third one is
okay. Good anyway. Okay. Okay. Good. Good try. Good try. Now. Okay, this is the figure that I have drawn except for the last one. Okay, all the other things are the things that I have drawn. Okay, now let me try to explain you. Okay, I'll give you 10 seconds here again. I'll give you 10 seconds here. Okay. Okay, yeah, somebody?
the
Okay.
charges present inside.
Hmm?
The charges, positive and negative charges present inside is equal to the, like when the charge get induced, all the positive side, when the electric field is applied, the positive sides get to the one side and negative charge get to the one side.
Hmm.
So uh, as given here, electric
Hmm.
internal is equal to E external plus induced.
Hmm. Right, answer is true. Answer is true. Okay. Now let me try to give you something here. Okay. Now what am I trying to do is, okay, I'm trying to give you a dielectric here. Okay, whatever, okay, please, okay, whatever I'm drawing, observe, okay. What am I saying is, I am talking about dielectric, okay. I have not finished yet, okay. Now, okay. So this is my dielectric. Now, in this dielectric, it's basically neutral, okay, because no external field is applied. It is neutral. Now, in this neutral electrically neutral dielectric, what am I doing is I'm applying some, okay, I'm taking a point, okay, this is my neutral dielectric, okay, and in this neutral dielectric, okay, I'm considering a small point, okay, I'm considering a small point, and I want to know what is the electric field at this particular point. Okay, is my figure clear? Is my figure
Yes.
clear? Right. Now
Yes.
in this dielectric, okay, at one particular point inside the dielectric, I want to find the electric field acting. Okay, total electric field at that particular point. That is why I am calling it as E local. That means local to that particular point, or internal, because internal, or to say inside a dielectric. Okay, I want to find out this. Okay, now when I want to find out this, okay, what am I doing is I'm trying to apply some external electric field, capital E. Okay, basically if the dielectric were not there, and if I'm applying electric field E, then at this point the electric field will be E itself. Any question?
So once repeat, please.
Yeah, if at all, if this is the point, okay, and sorry, right, okay, and if this point is outside the dielectric, okay, and if I'm applying an electric field E, okay, okay, so assume that I'm applying electric field E, then the electric field at this particular point will be E. Yes or no?
Yes.
Whatever applied field you have, that will be the electric field at that particular point.
Yes, sir.
Yes,
Now,
sir.
because of dielectric, what happens? Because of dielectric, what happens is, apart from the applied electric field, there will be some other electric fields also getting generated. Apart from the applied electric field, okay, that's what is shown over here. Okay, this part, okay, the last one part, E external. Okay, this is the applied electric field. Apart from the applied electric field, there will be three more electric fields that will be acting at this point when the point is inside the dielectric. If the point is outside the dielectric, whatever is the applied electric field, that will be acting. But when it is inside the dielectric, three more electric fields also will be acting. Okay, the combination of all these four is what you call it as the local electric field, local electric field. Am I clear?
Yes, sir.
Yes, sir.
Okay, good. The question is, what are these three extra fields that you got, sir? Okay, simple answer is, when I apply my electric field, the dielectric gets induced. Okay, that implies, okay, it will have some positive charges on one side and negative charges on one side, because of which there will be some induced electric field. Okay, he is representing it as EP. Okay, and it is in the direction opposite to the external field. Okay, and it is in the direction opposite to the external field. So there will be an induced electric field also. Okay, and you have already calculated that. Okay, you have already calculated that the net field inside the dielectric, okay, okay, is what you call it as E net. Okay, which is okay, external field minus the induced field, Okay, now, so that is what is your induced electric field, which is opposite to the external electric field. Okay, now what is this? Okay, this is this particular point. Okay, this particular circle or blue circle is nothing but this blue dot. Sir, but the sizes are different. Yeah. Okay, this is the magnified version of this particular dot. Okay, and this dot is as such magnified version. Okay, from the practical thing, that means actual thing. Actually, it will be very small. That means of the order of 10 to the power of minus 10 meters, or to say angstroms. Okay, 2-3 angstroms ఉంటుంది. Okay, that's small they will be. Here it is almost all okay, half mm, but actually in actual terms it is 10 to the power of minus 7 times smaller than the dot that you're talking over here, or to say shown over here. Okay, if it is 1 mm, okay, you're talking about 10 to the power of minus 7 mm, or 10 to the power of minus 10 angstroms. Okay, So that's what is the difference between, okay, -8 and God. Sorry, -8, okay. 10, 3, yeah, -7 only. Okay, right, whatever it is. Okay, so that's a magnified version, and this magnified version is again expanded here to this case. I'll talk about this later, but this is the case. Okay, now what's happening? What's happening is you will have different atoms over here. Okay, because of the different atoms that are present inside this particular okay dot, inside this particular dot. Okay, now this is my dielectric, and this central circle, red circle, not the dotted one. Okay, the central red circle is this particular red circle, and within the central okay, red circle there is another circle, that is this point. Okay, I'm talking about this molecule, and I'm trying to find out what is the net electric field on this particular molecule. Okay, because of the charges which are there in this particular outer red circle, okay. Okay, in this particular cube, what all things do you see? Okay, cube and some atoms at those 8 corners, and some applied electric field lines with the blue, and some induced field lines with the red, okay, in red color. And then you have a dotted circle to say that this is the region of importance. Okay, and you have two okay red circles, and these two red circles are magnified over here. Okay, on the right side. Okay, with the red blue line. Okay, this is the outer circle, and this is the inner circle. Inner circle talks about the atom or molecule, and this is a small region, okay, spherical region. This is a small spherical region, okay, around that particular, okay, point or point of concern or atom, right? Now, if you have different atoms or molecules here, then what happens is these atoms and molecules will get polarized, and the okay polarization results in okay some kind of charge distribution on the surface like this. Okay, sir, why did you draw okay pluses over here, and why did you draw okay minus here? Nothing, because I have taken my polarization vector in this direction. So polarization vector is from negative charges to positive charges. So I have drawn this, okay, from negative induced charges to positive induced charges. Okay, now this electric field, because of the charges on the surface, is as such given by P by 3 epsilon naught. Sir, how did you get this expression? Again, that's a derivation which is not there in the syllabus, so you don't have to worry. And if at all, if you are really interested, then okay, I can suggest you some. Okay, I can copy down and give you the derivation part here also. Okay, for the time being, so we have external electric field and then induced electric field, and there is some other electric field, because of the charges that are present on a spherical surface, considered around the point of concern. That means I have considered a spherical surface about this particular point where I want to find out the net electric field, okay, which you are calling it as local electric field or okay internal electric field. Okay, right. So the third term, okay, I know okay E external, that is E external, and then E induced plus the field because of the charges that are there on this surface. So this is the okay charges that are there on this surface, and because of these charges I have an electric field which is P by 3 epsilon naught, where P is the polarization vector. So you call this as okay EL. Okay, I don't know why okay this particular okay figure site, okay, that means to say I have taken this from this particular site. Okay, this figure I have taken from this site because he is representing it as EL. Okay, I have also represented it as EL, or else I would generally call it as E on the surface. Okay, that means because of the charges on the surface, what is the electric field? Okay, that's what is P bar by 3 epsilon naught. Okay, so one